Hey guys, this is Madhav. I'm following up on a video I was making in response to this meme by Hug and Chris talking about the plight of all high school students when they're forced to learn these random equations that all look the same but also kind of don't, and you don't know why it is that these are the way that they are. This is the second video I'm making. In the last video we talked about the difference between electric force and electric field. Now we're going to talk about electric potential energy versus electric potential. So let's start with electric potential energy. You're going to find that, as I hinted to in the last video, everything goes back to electric force. So the first thing to do with electric potential energy, understanding why is the formula like this, you're going to need to reflect back on what potential energy means. So potential energy, when you were dealing with non-electric things like balls that are falling down a hill, it's energy that could do useful work, but at the present moment it is not doing useful work. So for example, when the ball is at the top of the hill, it has a lot of potential energy that could be used to get the ball rolling. However, at present the ball is at the top of the hill, it has not yet used the potential energy. That's why we have this key relation between electric potential energy and work done. It just tells us that if the change in potential energy is positive, i.e. if the potential energy it goes up, well, that tells us that the work being done must go down. We're not using the electric potential energy to do useful work at the moment. We're storing it away. Conversely, if the electric potential goes down, electric potential energy goes down, then we know that work must be done, because now the potential energy, it's not being stored away to do useful work, it is actually going and doing that work. The other key thing to remember is how we actually define work. Work is a force applied over a distance, where, let's say you've got some box here, you're exerting a force that's somewhat upwards, and the box, it's on the ground, so it's traveling to the right. It matters what the angle is between the force that you're exerting and the direction that the box is traveling, which is why we have this cos theta term. So using these two relations, we're now going to be able to figure out how do we define the formula for electric potential energy. So let's get started. The first thing to note is people will, they will note electric potential energy as UE, and they will often write this without a delta symbol. However, note that there is no such thing as potential energy without comparison to anything. If you're raising a ball to the hill, the reason the ball is gaining potential energy is we're saying the ball is gaining height relative to some other point. You need that point of comparison, because if you just had empty space and the ball moves from one coordinate to another, can't say that the ball is gaining height. There's nothing to compare it to. That's why when we're talking about electric potential energy, here again, we need to refer to an electric potential energy as the difference in potential energy between some point and another. And when we write out, this thing without a delta symbol, what we really mean is, electric potential energy at some point relative to a point where there would be no electric potential energy whatsoever, a point with zero electric potential energy. How could you end up at such a point? Well, here's where textbooks have the most annoying phrase I've ever heard. They talk about electric potential energy when you're bringing a charge from infinity, which is a very odd thing to say. So let's say the charge is at infinity and you're bringing it from infinity. What does this mean? What it means is you're taking a charge from a place that is infinitely far away from all other charges. There's no other charges whatsoever, in the proximity of this charge is just so far away from everything else that you cannot have any electric force interactions. And then you move the charge from that distance of infinitely far away from all other charges to this new spot where there are other charges around that could create electric potential energy. So with all that out of the way, just we're gonna write in delta instead of just UE. Now delta UE, we know that potential must be, opposite to the change in work, so we can write this as the negative of work done. Conversely, you could put a negative sign here, make this a positive. It doesn't matter, we're just saying one of these is the negative of the other. Next up, we're going to expand this using the formula for work. So we have the force. In this case, we're talking about electric potential energy, so we're going to have electric force times the distance that the charge is moving times the cosine of theta, which is the angle between how the charge is moving and the electric force being applied. To make this more understandable, let's draw a little diagram. I'm going to erase this stuff over here. So, if we're going to have electric force being exerted on some charge, first of all we need that charge. So let's say this is our charge of interest. This is, let's say, Q1. If that force is being exerted on the charge, well, it must be exerted on the charge because of, the charge being in close proximity to other charges. So let's say there's a charge Q2 right next to our charge Q1. So these charges, because they're right next to each other, this is our starting state, and because they're both positive, then we're going to have a force that is pushing both charges apart. So the new end state of the charges is going to be that both charges have been repelled away from each other, because like charges repel. And the reason for this is that we have an electric force. So the electric force is pushing both charges apart. I will write Fe. Notice that the electric force, it's pushing the charges in this direction, this line, and the directions that the charges are traveling, it's also in the same line. So the angle between these two is 0 because they're moving in the same direction, just left or right. So if theta is 0, then cosine of theta, cosine of 0, that's just 1. So I'm just going to cancel out that term, that's just 1. Now notice something about the electric force. If you recall the formula we had for electric force, it depends on the distance between the two charges. Now, what is the distance between the two charges? Well, it is this thing right here. That's the distance between the two charges. Note something interesting. This distance and the distance that the charges are traveling from, being just right next to each other to now being this far apart, these are the same. D and R, these are the same things. So let's note that down. The distance that the charges have between each other, that's R, and from being right next to each other to being this far apart, the distance they have traveled is D is equal to R. D equals R. So now we're just going to take what we have and plug it in. That's all we have left to do. So electric force, we're just going to take this stuff over here and plug it in. And D, we're just going to replace with R. So D, we're going to replace it with R. You can see by multiplication this thing and this thing cancel out, and we're left with the formula for electric potential energy. So that's why the formula for electric force and electric potential energy, they look so similar. It's because the formulas, well, you just have electric force coming into the formula for electric potential energy. The key point to take away from this formula, what is it telling us? Well, it's telling us that the electric potential energy, the difference between the electric potential energy here and here, the change in electric potential energy, it's going to depend on the values of the charges involved. If you have larger charges, there's going to be more potential energy involved. Why is this? Because if you place two small charges next to each other, well, they're going to repel each other a little bit, so there's going to be a little bit of potential for work to be done, for movement to occur. If you put really huge charges together, then there's a lot of potential for the charges to move. Like, there's so much force just pushing them apart. So you can see why the electric potential energy should depend on the charges involved. Also, the electric potential energy, it depends on the distance between the charges. So if we started with this distance between the charges already, there's going to be less electric potential energy there, because there's less force pushing the charges apart, so there's less potential for the charges to start moving apart. Whereas if you start with the charges close together, then there's a lot of force pushing the charges apart, so now there's more potential for the charges to be moving. Now, I'll stop here, though there are more interesting things to think about when one of these charges is negative versus another is positive. Just the focus of this video is comparing this to electric potential. So look it up if you're interested, but for now let's move on to electric potential. So why is, why do this be? Why are the equations so similar? Just like before in our video on electric force versus electric field, we talked about electric field being a math tool. Electric potential is also a math tool. That is to say, it's not something that we'll measure directly. We can measure other things and then, use math formulas to compute the electric potential, but it's not just like this thing that exists in the universe without our thinking about it. To be more precise about what I mean here, so electric potential, it helps us predict what would the electric potential energy change be when a charge is moving from over yonder to over hither. What would it be if we were able to get rid of the effect of how large the charge is? So if you look at the formula for electric potential energy, just like we noted earlier, so if let's say we have a Q2 over here, and we wanted to note, okay, let's say you are moving some charge Q1 from over here to over here, what is that change in potential energy when you do so? Because there's less electrostatic force repelling these charges as they move further apart, so there's going to be a loss in electric potential energy, but we want to figure out what it would be. The issue is that our measurements, there should be a Q1, our measurements are affected by the value of this charge. We can't figure out, okay, in general, what is it, about this distance or this path of movement in particular that is giving us this reading. Our measurements are affected by the charge we're using to do the measurement in particular. So what we'd like to do is we'd like to figure out, okay, it doesn't matter what the charge is. It could be like 1 coulomb, it could be 10 coulombs, it could be anything. We want to figure out in general how much is the electric potential changing between this part of movement compared to like some alternative path, like so. So how do we do that? Well, the obvious thing to do is, okay, we want to get rid of the effect of Q1, why not just divide by Q1? That's exactly what we're going to do. Just on both sides, we're going to divide by Q1. If we're doing it on both sides, the equation doesn't change, it still holds. So when we divide it by Q1, we have now created something new. This isn't the original electric potential energy we were measuring. So now we have electric potential. Electric potential is it's written with a V as a symbol. You probably already know that, given that you're looking for some explanations about the equations instead of, an intro to the equations. But anyways, you have a V, just so that we don't miss out in writing it. I always call electric potential, I always call it voltage instead, because it helps me remember, okay, these things, electric potential energy, I don't confuse them as much when I'm calling one voltage and the other electric potential energy. So this is our formula for electric potential energy. Why is it the way it is? Well, think about what it's telling us. So this equation, it relies on the charge that is in proximity to the charge of interest, the Q1 that we want to be independent from, the charge we're doing to perform the measurement. So now it's telling us, well, if you have a really big charge around you, then you'll have a greater change in potential energy as you move from close to the charge to further away from the charge. Reason being because the electric forces involved are higher. And if you have a small charge, then not so much. Same thing with distance. So if you're moving from, right next to the charge to a point far away, then you're going to have a higher change in potential energy because electric forces over here right next to the charge are very high. Compare that to if you had a Q1 that was moving from a point already far from the charge to another point even further away, then the change in voltage, the change in electric potential energy per unit of charge, it would be lower because you're going from small to a little bit smaller, not as much change. Now, the last thing I want you to know about voltage is that people often use voltage to infer, what direction would a charge move. Like if you're, doing circuit analysis, people will draw things like, okay, here's a resistor, is there a voltage drop? Is there a voltage drop from this side to this side, or is it from this side to this side? Because that tells you the direction of current flow, the direction that charges are moving. What is this voltage drop thing? Well, voltage drop, it talks about voltage being reduced, right? Voltage going down. So the change in voltage, it is less than zero. In other words, voltage goes down. The voltage is decreasing. When the voltage is decreasing, what does that tell you? It tells you that the potential energy per unit of charge is decreasing. So the key thing about voltage is actually to think about electric potential energy. So if the electric potential energy, let's say it's decreasing from this side to that side of the resistor, that means that there's a lot of electrostatic repulsion over here that is pushing the electrons to this point over here where the electrostatic repulsion is very weak. So that's the key thing about voltage. That's why it's important. It's not important by itself. it's important as a shortcut to think about electric potential energy without getting too bogged down in, how much current, how much charge is actually flowing. Because if we get bogged down in that, then we have to compute values that are always changing in a circuit, depending on how much charge is there. But if we just think abstractly in terms of voltage, we get rid of this confusing parameter, then we can think about what really matters, which is it doesn't matter how much charge we have going through the wire at the moment. What matters is the electric potential energy is going down, whatever that charge is. You'll often see this drawn as a hill diagram. You have positive voltage over here, negative voltage over here, so you have a drop in voltage, and just like a ball rolling down a hill, you have a positive charge here. It's going to go just like a ball rolling down a hill, it's going to go from high voltage to low voltage. So I hope that clarifies some of the reasons why all these equations look the same. It's because everything is really based on electric force, and from electric force we get electric potential energy, and these things over here, these are just math tools that help us think about how the important stuff is changing without getting too bogged down in what are the exact charges involved.